This is lesson 2 of the first unit. We're looking at, from the notes, we are looking at part 2. You'll need your notes to follow along here. And part 2, it talks about an irreducible quadratic expression in the integrand. So suppose we had ax squared plus bx plus c. And suppose that this was irreducible, or you couldn't factor it. So let's talk about the process of completing the square. If I were to complete the square here, I would factor out an a out of the first two terms, and I'd be left with x squared plus b over a x. So that's if I factor it out of the first two terms, and I'd still have a trailing c. This, of course, should be review for you. Next, in effort to complete the square in this quantity here, I would take half of this value, half of the b over a, and square it. So I would have x squared plus b over ax plus b over 2a quantity squared, but in order to maintain equality, I would need a b over 2a squared here plus c. So now the idea is that I find a perfect square, namely x plus b over 2a quantity squared. That's the result of this perfect square. So what do we have left? We still have plus c, but we also have this a times this quantity here, which simplifies to be minus b squared over 4a. Once I have successfully completed the square, the strategy is going to be to let u equal this quantity that's being squared, and then to do a little bit of trickery where you let x equals u minus b over 2a. So initially that's going to be the strategy, and then we're going to talk about what happens after you do that strategy as we look at some specific examples. Here's example 1. Now when I first look at this example, my gut would say, ooh, partial fractions, and I would try to factor the denominator and would learn quickly that the denominator does not factor, which is leading me to this irreducible quadratic expression in the integrand. So to start off, before I'm not going to write equals, what I'm going to do is I'm going to look at the irreducible quadratic term, and I'm going to complete the square. So I have x squared minus 6x. I'm going to complete the square here, divide by 2, negative 3, square it, plus 9. So I also need a negative 9 and then a plus 13. There is no leading coefficient out here. So this factors nicely to be x x minus 3 quantity squared, and then the rest of the simplification is plus 4. There we go. So we've successfully completed the square. So now here's the strategy. We're going to let u equal x minus 3. And then, as I told you before, we're going to say that x equals u plus 3. And then another key feature is we have to find dx. In this case, dx is going to equal du. Now we're ready to make the substitution. And so I have in the numerator 2. Instead of x, I have a u plus 3 minus 1. And then in the denominator, that's going to be not the original, but instead you can see that's going to be u squared plus 4, because we let this value here be u. And then dx is also du. And now we're ready to go. Now it becomes good old-fashioned traditional integration. So we have 2u plus 5 simplified, and we have u squared plus 4 du. Now, how do I integrate this? Well, this is like one of the ones in the integration extra credit problems that you did. And the trick here, there's a couple ways to do it. Perhaps you could try a trig sub. The easiest way is to break this into these two fractions. Common denominator is already there, so you have 2u over u squared plus 4, and then we're going to add that to 5 over u squared plus 4 du. That's probably the easiest way to do this. Now, finishing it off, the integral of the first one would be a traditional u substitution, and after doing that traditional u substitution, we're getting natural log of u squared plus 4. Plus, you may recognize this as, I'll come over here with a little note. If I factor out a 5 over 4, I'm left with 1 over 1 plus u squared, which is arctangent. So we have 5 fourths. Let me back up here. This is actually going to be u over 2 squared. See, if I factor out a 4 out of this, I need an over 4 and then a quantity u over 2 squared. So with a u substitution here, I'll say a w substitution is u over 2. That's actually going to change this to be 5 halves. So we have 5 halves arctangent of u, actually of w, plus c. Sorry for the confusion. So then it's natural log u squared plus 4 plus 5 halves arctangent of u over 2 plus c. Now we're going to convert this all back in terms of x. So this is going to be u squared plus 4, but u squared plus 4 was defined over here, and we know that that's the irreducible quadratic. So x squared minus 6x plus 13 plus 5 halves arctangent of, our u is x minus 3 over 2 plus c. That's the end of example 1. Moving on to example number 2. Okay, same deal. We have an irreducible quadratic factor. You would discover that if you tried to factor this. That's an 8 if you can't read it, and that's a 25 if you can't read it, but it's also in your notes. So let's take this quantity and complete the square. So I have x squared plus 8x. Half of that is 4. Square is 16. Minus 16 plus 25. That's going to give us quantity x plus 4 squared plus these values here, which is 9. Okay, do you know the strategy? I would press pause and try to do this on your own. It's actually fairly easy and fun. U equals x plus 4, excuse me, x equals u minus 4, and dx equals du. Okay, so now the integral 1 over radical x squared plus 8x plus 25, ooh, that is sloppy, equals, let's take a look at this, that's the dx here, so it's going to be du over the square root of u squared plus 9. Okay, now how do I solve this? We're back to traditional techniques. It looks like we're going to need a trig sub. U equals 3 tan theta. Du equals 3 secant squared theta d theta. Substitute in, and we have 3 secant squared theta d theta for the du. And the denominator, I have 9 tangent squared theta plus 9. Continuing along, this is review for you here, so I'll move quickly. Secant squared theta d theta over, so I factored out a radical 9 to cancel out the 3. And I have now over the square root of tangent squared theta plus 1. Okay, so now moving along from there, that's going to equal, well, here this is an identity for secant squared. Then I'm taking the square root of secant squared, which will give me secant on the denominator together with secant in the numerator. Secant squared in the numerator will simplify to secant of theta d theta. This is book of memories. Do you have this committed to memory? This should be natural log, absolute value, secant of theta plus tangent of theta plus c. Now we're going to back sub a couple times here. So this is going to be first in terms of u and then back in terms of x. So this is going to be natural log of the square root of x squared plus 8x plus 25 over 3 plus x plus 4 over 3 plus c. Now where does that come from? Back to here where we said u was the 3 tangent theta, and here's theta, so tangent of theta would be u over 3, and this quantity here would be u squared plus 3 squared. The secant would be u squared plus 9 over 3, and this is, well, u squared plus 9, or rather the square root of u squared plus 9. That's better. And then tangent of theta would be u over 3, or x squared, or sorry, x plus 4 over 3. So there it is. Now if I was putting this into calculator form, I would write it as natural log square root x squared plus 8x plus 25 plus x plus 4 plus c, because I could write that as natural log of numerator minus natural log of denominator, which is natural log 3, which then gets embedded into the c. So that's the calculator form.